Then, so today we'll be talking about getting started with AI in the Wolfram language. I'm Maximilian Gerard. I'll be presenting this webinar to you today. I'm a technical consultant here at Wolfram, so I work on external client projects, and that's what I do here. And today, yeah, AI. So let's get started. Here's a brief outline of what we're going to be covering today. So this is quite a broad introduction. There's quite a lot in the field of AI, so that's quite a broad topic. So we're going to start off by just going over a few of the basics of the Wolfram language itself, just very briefly to make sure that everyone's up to speed. Now, mind you, you should have access to this notebook. So if you have downloaded it right now, you can go ahead and follow along on your own computer and evaluate the examples as they come about. If not, don't worry, you can access the materials presented here today at a later moment. So if there's anything that goes over too quickly, you can go over it in your own time. So we'll be going over a few of the basics of the sort of the Wolfram language, a bit of the syntax, just to make sure that everyone can sort of follow along. And then we're going to be talking about how it pertains specifically to machine learning. We'll be going over some examples and sort of like discussing what exactly we're talking about when we talk about AI and machine learning, which are sort of similar, related, but not quite exactly the same. Then we're going to be talking a bit more in detail about feature extraction, and then classification, prediction, and then finally we're going to finish off with a quick tour of what neural networks, what kind of functionality we offer for that. If at any point you have any questions, please do post them. I'll do my best to get to them. So that should work both through BigMarker and YouTube. So I'll do my best to monitor those, but if not, I'll get to them at the end if we have time. So with that being said, what exactly do we mean when we're talking about AI and machine learning? So typically, what we have in the context of machine learning is that we need to, in order to actually produce something computably, we need to have what's called a model. And so typically that's going to be a program or a set of weights and parameters. So the parameters is a word that comes about often, and they have different meanings depending on the precise model that we're talking about. But that's what we're trying to produce. We're trying to produce a model so that we can then make use of this in a programmatic fashion. And then there's this notion of learning. Reason being that the model itself, it needs to sort of the parameters need to be learned based off of data. So that's sort of the workflow. We have some data, and then we want to produce a model based off of the data that's going to try and understand it, replicate some of its features. That's data converted to model. And there's a lot of subtleties as to how you train the parameters in your model itself, and how you even choose what model you're going to be using, and then how you go about converting that data into something that's actually computable. Because what does an image mean in terms of data, right? If it's data points on an XY plane, that's that's numbers that you can operate on. But there's a bit of work, and that's the feature that we're talking about in terms of feature extraction for things that aren't quite so encoded like numbers are. So that's sort of the brief overview, right? It's all about models and about parameters and about dealing with data. And mind you, sometimes we're dealing with very large amounts of data. So if you're running some of these examples yourself, be warned that there might be a bit of expensive computation involved. So it's not quite so snappy or instantaneous as you might expect. Now, broadly speaking, you can sort of categorize different types of machine learning into three categories. So supervised learning, unsupervised learning, and reinforcement learning. And further to that, supervised learning can be broken down into two different types of learning. So supervised learning is when we have input-output pairs, right? So where we have in the data set that we're producing or that we're making use of, we already have sort of mappings between, we know what we're expecting or what we would want our model to produce. So if we go back to this example above, here we have an image, right? So that's the input. And then we have cat here as a label, and that's our output. So this is an example of a supervised learning problem, right? And here in this case here, where we're trying to sort of match a curve to these XY points, well, actually our input is the X variable, right? So here that would be minus 0.5 or 0.5, 0.6 here, and our output is going to be the Y-axis. So here in this case it's going to be 0, and then here in this case it's going to be -1. Because the origin is not here. The origin is actually up here near 0. So that's these two here examples of supervised learning. And examples of that include image recognition, and this is actually the most common type of artificial intelligence that we're dealing with, supervised learning. Now, there are other kinds of so less common types of learning, which is, for example, unsupervised learning, where we only have inputs, right? So that's going to be clustering problems, or where we're trying to find patterns in unlabeled data, or if you're trying to, for example, generate images. There's still some learning involved, but it's not quite. It doesn't have these sort of. There's the output that's missing from the input-output pairs. We only have the inputs. And finally, and we're not going to go over this today, but there's reinforcement learning. And here there's this idea of a sort of a feedback loop between a model and its environment. So that would be trying to learn how to play games, for example. That would be an example of reinforcement learning. And there's this notion of reward, but yeah, we're not going to cover that in detail today. So we'll mostly be talking about these first two, supervised and unsupervised learning. So here's a few examples of typical tasks that come about in, that exemplify this. So classifying of images, here an image of a cat and a label of cat, or predicting a variable in the data set. So in the example above, we had just one variable where we just had some arbitrary x, but here, for example, we might have the age of a person as part of the input along with their sex or their gender, and we're trying to predict, for example, a height. So that's a data set where we're trying to predict just one variable. Another example would be translation, where we're going from text to text. We have to think a bit carefully about how we go about encoding this, this input as text. Or as another example where we're sort of predicting how a time series is going to progress, or predicting anomalies, for example, in a time series or in a non-time series. Right? So that spike would be we're trying to detect here for those events. And we mentioned about unsupervised learning. Data clustering would be one such example, right, where we've got a bunch of data and we're trying to figure out where, how we might be able to classify or bunch them together. Now, this solving a maze would be maybe perhaps more an example of a reinforcement learning algorithm where maybe we have some environment such as a maze and we're trying to navigate it, and maybe we have a certain amount of energy or some amount of information that we need to collect about the maze as we're navigating through it. But yeah. Great. So with that being said, let's first do a bit of a quick introduction for those of you who may not have used or may not be super familiar with the Wolfram language itself, just to make sure that everyone's on the same page. So this here is a notebook, right? This very window is a notebook interface, so that means that I can do computations. So you'll see me doing this as I go along. I'll be running and executing code that's within this presentation itself. So that's sort of what we're dealing with here. This is a notebook. This is also, we're dealing with both, traditional numeric computation, but also symbolic computation. So what that means is we can reason about things symbolically. So for example, I can ask to solve something such as, let's see, x squared is equal to 2. And we'll see that, x here is returned as a symbol, right? This expression makes sense in and of itself, even though we haven't defined what x is. So that's what symbolic computation means. And this is, it actually plays quite nicely in terms of the way in which you can represent data, such as neural networks and models themselves symbolically within the Wolfram language. So there are some advantages that we'll go over in the context of artificial intelligence. Within Wolfram Alpha, I don't know if you've heard of Wolfram Alpha, but we have some natural language understanding. So we make use of artificial intelligence for some of our products, and we make those available through some of the classifiers and models that we'll go over later. We also have state-of-the-art algorithms. We have built-in data. This is quite useful, actually, for you'll see it used throughout the documentation. If you look at those functions definition pages or documentation pages, you'll often see us making use of our own example data sets and knowledge bases. But yeah, we also support a whole load of formats, and that's quite relevant in the context of machine learning, given that we're dealing with sometimes quite large databases, and we put a lot of effort into making sure that we support whatever data you might be trying to import. And as I've already mentioned, our documentation is really powerful and is, in terms of being both sort of an area, the go-to place in order to understand how a function works within the Wolfram language, but also for actually explaining the underlying concepts. We make sure that we put a lot of effort into making the documentation be sort of take you from no understanding at all to going to some quite interesting and advanced examples. So I for one, quite enjoy using the documentation. So that's a sort of a brief overview of the sort of the different things that we do and that might be relevant to here today. Now let's briefly talk about the syntax so that we don't get too carried away in terms of seeing some fancy stuff, some fancy code that might be a bit confusing. So within the Wolfram language, so this is the Wolfram language that you saw me evaluate above and that we'll be exploring today. The syntax is to call a function, you write its head. That's what it's called here, which is sort of the name of the function typically that you're calling. A built-in function will have a capital letter, such as a capital H head. And then to call it, we use a square bracket, and then the arguments are separated by commas. Right? So just that's how that works. And then sometimes you can also provide optional arguments, and those are specified by giving their name and by using this arrow here, which if you want to type an arrow, you type in the minus symbol and then a greater than symbol. And you notice that that has been automatically ligatured. I don't know if that's, this is a ligature. It's automatically converting it into this sort of this character. As you see here, this is, so it gets broken up. So that's how you specify that you want to make use of an option. So yeah, so that's sort of the syntax for calling functions. In terms of data syntax, that's where we see these curly brackets come about. So that's for lists. So lists will be defined of that sort. Lists, they don't have any sort of limit or depth in the sense that this doesn't enforce, lists in themselves don't enforce type. So you can have nested lists of lists that are ragged, such as this. In fact, you can actually have different types of elements within lists. So here we have a number, and then we also have, where's my quote character? There we go, a string. In fact, we can also have an arbitrary symbol, right? So these in fact, let's make a list of a symbol. So that's perfectly allowed. So that's sort of lists within the Wolfram language. And then we also have associations, or sometimes those are known as, or equivalently seen as dictionaries or hash maps or key value data. And the syntax for that is a less than symbol, and then a pipe symbol, sort of this vertical bar, and then keys separated, keys and values separated by commas, and with, again, this arrow between them. So that's sort of the associations. Then if you want to access an element from that, you can call it as if it were a function, and then pass the key that you're looking for within these square brackets. And so if I evaluate this, we'll see that we get this name back here. And again, we can have nested associations, and then that's no worries here. And in fact, you can mix between having lists of associations and associations of lists, and any arbitrary construction that you might want to have. Now, there are also this notion of data set and tabular, and these are special constructs that are sort of making, giving some helpful tools in order to both be able to better visualize data sets. So if you create a data set object, it'll be formatted in a nice way in the front end, which can allow you to sort of interactively explore data. See how there's sort of this URL bar style thing. So you can explore data in that way, and there's also some nice query syntax to be able to do some powerful computations on the data set itself. So that's for data sets. We'll make use of those tersely, but it's worthwhile mentioning them in the context of artificial intelligence, given that they can be quite nice. And tabular data, which is particularly relevant when you're dealing with very large amounts of data. They're more restrictive in the sense that they enforce a sort of tabular structure, which is to say that there's database SQL-like columns and rows. So all data within a certain column will have a consistent sort of type associated with it, so it's more restrictive, and therefore that allows for more efficient representations in memory. So those are the kinds of things that we're going to be dealing with in terms of data. Great. So in terms of how this is going to be relevant, or what we're going to be doing within the Wolfram language that deals with machine learning. So there is no library. All of these functions are sort of built in. You can access them immediately. So these are the sort of the built-in functions that we're going to be dealing with today. So we mentioned earlier that there were, in the context of supervised learning, there was these are two relevant functions for that. So classify and predict. here are some clustering functions, dimensionality reduction, and feature extraction functions. So the list goes on and on. There's a whole number of them that you can, in fact, these will bring me to links to the documentation online. And in fact, you can either access the documentation, it's opened on my separate window here, but yes, I've clicked on this link and it's opened up the web documentation for me here. If I can change my window size a bit, so let's see. Yeah, so this is the documentation that's available online. Otherwise, you can also open it up within your local documentation if you've done so. What I've done here, so I've selected my function here and I've said help find selected function, and that'll bring me directly to the relevant function page, and I'll maybe show a few examples of that because I quite like some of the examples that are presented there. So yeah, all the built-in functions have their own documentation page, and they go about showing how you use them and with some relevant examples. And so all of them, you'll notice that, for example, if you're familiar with classification or prediction, in the context of classification, there are a lot of different methods for how you do classification. Maybe it'll be k-nearest neighbors, or maybe it'll be support vector machines. We don't have functions for the methods. We have functions that are oriented for their use. So there's one method for classify, and then if you want to specify what actual algorithm or method you're going to be using, that's going to be using this option syntax that I mentioned earlier. And so that's nice because it means that there's sort of a uniform way of making use of and calling these different functions. And so you can play around and experiment quite easily by, we've made it such that you can change method quite nicely and quite easily. So that's sort of the value proposition of the way we've set up Wolfram Language in general, but machine learning in particular for how to, Wolfram Language. The Wolfram Language way, the Wolfram way. And then there's also the sort of the neural network framework, and there's a number of functions in there, nettrain, and I'll go over them in more detail towards the end. Great. So let's start by just doing a few examples of actually doing some basic AI machine learning examples. So here we have the first task of classifying a language. So here's our input, and we want to sort of predict the language of this piece of text. So you'll notice that classify, if we go to the documentation of classify, normally you give it the data that you want it to train on, but there are a certain number of classifiers that are built in, right? And so this is one of the list of such things, and you'll notice that here we've chosen language as that classifier. And so if we evaluate this, so quelle est cette langue? I happen to be French. We can see that it is correctly classified this as French. And in fact, we can also ask not just if we specify as a second argument the top probabilities, we'll see that this will also give us not just the language that it's predicting, but it's sort of probability. Now, mind you, this is not a formal probability in the context of mathematics, but this is a sort of an indication of how confident the network, or rather the model, is that this is the correct language. Right, so that's a quick way of how you can immediately make use of some of the built-in neural networks, or rather models, classifier models that are within the Wolfram language. So it can be quite useful to just have those immediately available. And here's another example in terms of classification. So, here, two more examples. We have a wolf and a lime. And here we're using the image identify function, which is, again, another built-in function. Here I've just opened up the documentation page for it. And we're just applying this, so mapping this over the two elements that we have here. So we're doing image identify of wolf and image identify of limes. Now, you'll notice that I don't actually have the model, because there is a neural network involved in this image identify model function, rather. So the image identify function makes use of a neural network, and the weights for that model, I didn't have them downloaded, at least not on this machine, and it's gone ahead and downloaded those. And under the hood, maybe you saw those little images flashing below showing a download progress. And once it's done those, it's actually gone ahead and ran the classifier, and you see that it's gotten a wolf and a lime. Great. Instead, we can, so the image identify model makes use of one of our built-in trained models, but we can also specify a specific model, right? So this happens to be the Google LENet, and there's in fact a Wolfram function, neural network repository. And if you're interested in any of these, or if you're this goes beyond the sort of built-in functions that we have here. And so there's a whole list of different networks that exist for classification, for prediction, for whatever have you. In fact, they're classified by what they propose. So classified by input domain. So there'd be audio, numeric, or different task of types. So you can go and explore those. But as an example here, we're going to call NetModel on this Inception v3 neural network. And as you see, it's downloading it. This happens to be 100 megabytes, so not inconsequential. And then we can, again, see and compare the results with our built-in image identifier. And so whilst that's downloading, it's worthwhile noting that, well, we'll go over this a bit later in detail, but because the models themselves, you can actually access the weights and inspect them and see how they operate. Notice that here it proposed lemon rather than keyline, but that's how you go about making use of the built-in functions and built-in neural networks. There are some other things that we can do with regarding images. So we can call this sort of image restyling. So we have 2 different artworks. In fact, we have 3 different artworks. And we can call this image restyle function. So we're taking one of them and then we're adapting it to be in the style of another one. So this is sort of relatively recent, well, maybe not quite so recent, but one of the interesting neural networks or that has come about in the last few years. So here we have a rendition of the Mona Lisa in a different style, or in the, in fact, yeah. And again, this is a built-in function. Now this is perhaps less neural network oriented, but we have some other built-in text functions for artificial intelligence here. We're breaking down sort of grammatically, syntactically, or not semantically, but syntax. So this is the different syntax of sort of the building blocks of this sentence, where we see that we have verbs and adjectives. And so text structure, that's one of the functions that are built in. And as with most functions, you'll find that there's you can call for more specific detail. So you can ask for a specific part of speech, but you can go and look at the documentation if this function is relevant to you. Now we also have quite a nice whole system built around quantities. And this is quite useful in terms of doing computations. For example, I can ask about, in fact, let me just quickly demonstrate that. If I type an equals symbol, or if I type equals square brackets, I can talk about particular units. So here, this is doing a freeform input. I can type whatever I want here, and this will run it through an interpreter and trying to construct a Wolfram language code that will correspond to this. Now, mind you, this has been queued after the text cases. So this other result is running. So I'll go and find in the documentation what that looks like, because those are sort of statically generated. So this is what I would have expected it to construct. If I'd have written, if once this 10 kg evaluation evaluates, it will return something like a quantity, right? So here it's not just a number, but it's a number that's tagged and associated with a particular quantity, a particular unit, right? So here, kilograms or meters. And this is useful because you can sort of do computations on them that are sort of unit aware. So for example, I can ask if 16 ounces is equal to 1 pound, and that happens to be true. Or I can do some additions and multiplications, and it's all unit aware. So that's very nice. And the reason why this is being brought up here is because we're downloading data from a Wikipedia page here about the moon. And then we're using the text cases function to identify the areas within that Wikipedia page where any unit was measured, or rather where any quantity was specified. And so we'll see that, for example, here, this, I don't know if this perhaps corresponds to the distance I expect from Earth, or maybe its period, or yeah, so those are all the units that have been identified in that Wikipedia page. And we can also use the text cases function to find the most common words that were brought up. So the surface and side were some of the most common that appeared there. We mentioned earlier anomaly detection. So quickly, a few examples of this. Now notice that these are colors, right, that were built in. In fact, they have different RGB components, and most of these are sort of a bluish, purple, pink, and except for this red and this green. And in fact, the find anomalies function has, in fact, identified that these sort of stand out. And that's quite interesting because, you know, colors you wouldn't necessarily expect. So there's some sort of nice built-in feature extraction that's built in here that we'll go over in just a moment. Now this also works, we've seen it for colors, but it also works with images. So This MNIST database is a very common one that's brought up in the context of machine learning. The MNIST database is a set of handwritten digits that the American government, I believe, produced in the 80s or 90s, and has been used as a sort of a standard classification problem to sort of identify which of the 10 possible classes, so the digits 0 through 9. Right, so we're trying to identify, that's the problem of the MNIST database, trying to classify the images to identify which digit it is. But here we're using it in this sort of anomaly detection, and that's the context in which we're bringing it up here. So we've gotten this, database, this MNIST database is built in into the resource data, so we can just immediately have access to it here to play around with some examples. We're accessing the images themselves, and then we're taking a random sample of 1,000 of them. And we're creating this anomaly detection function, right? So here we just specified, oh, just find the anomaly in this data set. That works in this context, but it works actually better if you already tell it, this is the kind of data that I expect to be normal, and then here's some new data that you haven't seen. Is it any different, or are there any anomalies in the new data set? So here this detector function is been prompted on sort of normal samples of the MNIST database through what we've written about here. And here we're asking it in this new data where 2 of the such samples are anomalous. And in fact, it does correctly find that this digit here is a 4, or it's meant to be a correct digit, but it's been sort of mangled. And here's just a completely irrelevant function. And so it correctly identifies those 2 as being anomalous. And so there's some nice automatic things that have been done here that we didn't have to do too much work, but we'll dive into the details of specifically how feature extractions works shortly. And in fact, that's what we're going to cover just right now. But yeah, so that's some examples of how to use the functions related to anomaly detection. Great, so feature extraction. What does that mean? Well, in the context of dealing with computation, all these models, they kind of need to operate inherently with numbers. Right? In order to be represented by computers, we need to have numbers. And so you can't directly operate on text. You can't operate on colors or images. So that's what it means by feature extraction. And in fact, we do have some built-in feature extraction functions. So here's a few examples of how that might be converted, right? So if this is, for example, an input, and we might want to do some further work on that in the context of classification or prediction. In order to be able to operate on it, we need for it to be converted into a sort of vectorized, right? So converted into a list of numbers. And in fact, here we see that it's decided the feature extract has produced 3-dimensional, that is to say, a list of 3 numbers for our features. Now, that needs not be important to note is that this is a lossy process typically. It needs not be, but typically it is, right? You can't reconstruct, in this case, the inputs based off of just these 3 numbers. Now, actually, that is usually relevant because you don't actually need all the data in order to be able to correctly do some classification or some prediction. You just want to be able to focus on the most important parts. In fact, typically, increasingly so with the sort of large amounts of data that we have, we want to sort of be able to get the signal from the noise. So that's kind of a big important aspect of it, is the feature extraction. Now, the feature extraction function works on, here's an example where it was 3-dimensional features, and here this is 2-dimensional features. And I believe, in fact, you can probably specify how many, the dimensionality that you want, or the method that you want to, how you should go about doing that feature extraction. But conveniently, the Wolfram language provides a bunch of standard methods for extracting features, be it for text or images or colors or videos. So you can very easily, you don't have to necessarily worry too much about that step, though it is a very important one. And in fact, here we're also extracting features off of graphs. Now, it's important to note that those aren't necessarily going to be standard features like you and I might understand. So for example, for this graph, maybe we're going to be interested in sort of a description of it in a sort of a human-centric way. So maybe we're going to talk about, I don't know, how pointy it is, or maybe its graph diameter in terms of the minimum number of edges to connect the 2 furthest apart nodes, right? So when we're extracting these features, that's not going to correspond to features in that kind of way. They're sort of going to be a bit more ambiguous, right? They don't necessarily have meaning like we would, like us humans would come up with them. And it's also worthwhile noting that if, for example, in our inputs here, if we had, for example, height and length, it might not actually be relevant to directly maintain both of those. Feature extraction might mean discarding some features that are correlated with others, or in fact combining multiple features into one, because the information that's provided is linked. So yeah, that's what's going on here with feature extraction. And that's the first step of what's going on. And oftentimes it's sort of hidden when you're using these classifier and predictor and all these high-level functions. They're making use of feature extraction under the hood, but they might not be visible to you. But that's the important first step in terms of starting to operate on your data, is converting it into features, into numbers that you can actually operate with. Great. So here's an example of what the kinds of things you can do once you've extracted features, but with a concrete example. So here we're going to be focusing on some of the characters from Guardians of the Galaxy, specifically these four, so Rocket, Raccoon, Groot, Gamora, and Star-Lord. Now you can extract these using the web image search function, but do note that those use service credits, so we've actually just built those in directly into this notebook here. So this character images contains itself some of the images. So just show off what that looks like. Let me just do a random sample of, let's say, 10 of these images. Now, in fact, this is a list of lists, so I need to flatten that first. Great. So here are 10 such samples from this list character images. And so this is the kind of stuff that we're dealing with. Now, mind you, we have a first list, which is just 20 images for the first character, and then another list, which is 10 images. So this is this dimensions here. So it's a list of 4 lists, each with 20 elements. So for a total of 80 images in total. So that's the sort of what's in this character images variable at the moment. Great. So we're going to reshuffle them. So that's what this. If we don't specify how many, this random sample function just reorders them in a random order. That way we're not sort of letting on any information about that. And now we're passing it on to this feature extraction function. So it's creating an extractor function. And that'll convert it into sort of this vectorized representation that we're seeing here. And it's, in this case, decided that 79 numbers was the correct sort of dimensionality for this. So this is what this particular image would then get converted to based off of the feature extractor that we've created. Great. So now that we've done this, we can start actually doing some stuff with it, right? We can actually start doing some computation. So what that means, for example, is we can use this feature nearest function, which will do this effectively this notion of distance within a vector space. So in 2 dimensions, it's literally the length of the shortest line, and that can generalize to higher order or to higher dimensional vector spaces. So here, in our case, our 79 dimensional vector space, and that's what this nearest function does, right? So we can now, in fact, it's using this notion of distance to find the image from our original data set that is closest to the image that we're providing here. So we're taking this image, using the feature extractor to convert it into a vector. We're finding the closest vector to that from our original data set and finding the image that created it. And so this is what's going on. And this is sort of we can see from the fact that these 2 images to us humans look quite similar, that this extractor function is producing something that's actually relevant. So these 2 images that are similar to us as humans end up being close in this feature space, in this 79-dimensional vector space. So sort of a good qualitative assessment that our features are corresponding to what we want. In fact, they're both from the same character, and they in fact have sort of similar kind of poses or similar kind of compositions in terms of the images themselves. And again, the feature extractors there are some built-in ones that are using various techniques based off of if it's a sound, if it's images, if it's video, and so that sort of speeds up the work, and that's why these are working the way that they do. Great. Now we can actually try and do a feature space. In the case that we were showing above, it was 79 dimensional, but we can actually reduce that down to just 2 dimensions, and then use those 2 components, right, the x and y component, as a way of plotting in 2D space. So this is what the feature space plot function does. Now, 2 dimensions is rather little, and in fact, we're sort of it's getting quite crowded effectively, right? So you can't. It's going to be hard to reconstruct or to make much sense of. There's going to be a lot of images that are close together that might not actually be that related. But we're seeing that there's maybe similarities in terms of colors, in terms of composition, maybe in terms of characters. So there's some amount of sense that can be made. So these 3 are quite similar, both to us humans and in terms of where they're placed in this feature plot. And that's again a neat way of qualitatively saying that our feature extraction is working as intended. Now this function here is this feature space plot function is very neat because we just gave it our list of images, and we gave it how this is just purely to decide the size of the points themselves. We didn't have to do any work, but if we wanted to construct it ourselves, we would make use of this dimension reduce function, and that would then be something that we can use here in order to in our list plot. All right, that's going to produce a list of XY coordinates. So if you wanted to do under the hood, so again, these are quite high-level functions. In fact, it's produced a different embedding of the images, but that's how you would go about producing it yourself, and then making use of the list plot function with plot markers. Great. So that's sort of how feature extraction is, how that works. And here, so this would be an example of unsupervised learning, right? Finding sort of clustering or maybe dimensionality reduction. That's one such example of unsupervised learning. We've not done any prediction or classification yet, but that's what's next, right? So classification. So you'll recall that the I think this actually, if I'm recalling, yes, this is sort of classification. Before we get into how classification pertains to the example that we were seeing from Guardians of the Galaxy, first let's sort of go over the typical kind of workflow that's relevant to this. So as a reminder, classification, we have input and output, right? With this sort of, in fact, let me just go to the documentation since this is what I'm talking about, right? We have each element from our data set has an input and a tagged class, right? So that's classification, and the classes themselves need to be discrete, right? So there's going to be, in this particular example here, this is the input. We have an input 1, an input 2, an input 3.5, and input 4, and the classes are A and B, right? So it can't be a continuum. It can't be like a number like 3.2. It needs to be discrete classes. It can be true or false. It can be cat, dog, or it can be, maybe any number of things, but those need to be discrete. So this is the distinction between classification and prediction, where prediction is going to be a continuous class, or it's no longer a class, but sort of a predicted value. So in terms of the sort of approach that you take, typically you start by importing or pre-processing your data, and that will include the feature extraction. And then you create a classifier, or you create a model. You specify how you want your classifier to function, and then you train the classifier on the data. So that's going to be figuring out the weights or the parameters to your model. And then you're going to be testing it on your testing data, because in fact, it's a bad idea to train the classifier on all of the data. So you break it up into training and testing data. That way you can sort of, because the issue is sort of, the analogy is, when you're testing as a student, if you're learning a new concept, you don't want the test to just include things that you can all learn by heart. So if it's a definition in mathematics, or if it's a piece of fact that you need to remember, then yes, it does make sense to test on something that a student will have learned. But if you're trying to teach sort of a method or a process, such as, I don't know, factoring polynomials, then you don't want a student to be tested on a polynomial that they've already solved, because they can just remember the correct answer, right? So that's sort of the idea that's going on here. You break up your data into training data and testing data. So the training data is actually used to train the classifier to compute, to learn the parameters. And then you can actually test it on data that it hasn't seen before. Right? So that's an important aspect of it. And then once you've done that, you can sort of measure you can sort of see how well your classifiers are actually doing, and perhaps you're going to, from some of the insights you're going to gain there, perhaps you're going to decide that you want to adapt the way that you've done your training, or maybe you actually you realize that you want to change the classifier itself. You go to a different choice of model, or in fact, maybe you realize that there's actually issues with the data itself, and you might need to go and collect some more data. So it's this is presented in a very linear list, but in practice, it's a rather non-linear process. There's a lot of back and forth depending on what you're doing. And the kinds of classifiers and methods for learning and work is very dependent on the nature of the data itself and what exactly it is that you're trying to do with it. So this is the standard approach, but it gets complicated. So let's run through this in the example that we were doing earlier with our characters. So here we're sort of using this. We've got a lot going on here in terms of flattening and threading. And what that looks like in the end is it's actually just converting. Let me just do our character data, and let me just take the first 3 samples from that. Or in fact, why am I getting more? Has this been flattened? I'm surprised. Why am I would expect. I have requested 3 elements, please. There we go. I forgot what I didn't know what I wrote there, but this is what I'm expecting. So our character data variable now contains a list of rules, right? We have an input and an output, right? So they're all labeled, right? So this is labeled data. That's what's in our character data function variable. And now we're defining, mind you, we had 20 images per character, and we had 4 different characters. So we have a total of 80 images in our, training points in our character data variable. Right? And so we're doing this distinction here where we're breaking it up into a training set and into a testing set. So where the first 60 elements are part of our training set, and then the next 20 are in our character data, in our testing set. Great, so that's the first step. Great. Now, once we've done that, we can just pass along our training set to the classify function. And notice that that's sufficient in order to build a classifier function. And you'll see that it's correctly picked up that there are 4 different classes, and the input type is just images. So it's actually dealt with converting. We were messing around with different types of feature abstraction earlier, but it's sort of made abstraction of that, and it's made its own. All of that is sort of built in to this classifier function that's been constructed from the classify method. And in fact, you'll notice that it's in fact made a choice of method. We've not spoken about the different methods, but it's chosen logistic regression for us. So this is quite neat. That within the Wolfram language, the whole 2 steps of creating a classifier and training it is literally just calling one function. Now, once we've done that, we can test it. So here's a new image that wasn't a part of our training set, and we can just call our classifier function as if it were a function, because it is, and see that it's correctly identified that it's that this character here is Rocket Raccoon. And in fact, we can ask for more of this. So if we asked for the, let me find my keyboard for top probabilities, we'll see that it's very confident that it is Rocket Raccoon. And it says that it's extremely unlikely to be any of the other ones, right, with these very, very small numbers. Now, mind you, again, this is not, these probabilities aren't formal probabilities, and it actually does also get things wrong. So here it's correctly also found correct classification for this other character, but it isn't always right. And in fact, so here what we're doing is we're extracting 5 elements from our testing set, and we're passing it along to our classifier function, and we're seeing that it incorrectly identified this image as it's not, this is Groot, not Rocket Raccoon, and it's correctly done a job on this one. Same for Star-Lord, but here again there's another mistake. So it's it's trying, but you will get measurements mistakes or misclassifications, and in fact that's exactly what's going on in terms of the last step that we were talking about, which was getting a measurement for how well your classifier is actually doing. And in fact, we have a built-in function for that called classifier measurements. So what we're doing is we're calling the classifier measurements, we're giving it the classifier function, and then we're giving it the testing set. And so it's producing statistics, or it's building measurements for the classifier on the testing set. Because again, it doesn't make sense to test or to measure the performance of your classifier on the training set on which it was trained. So let's quickly run through some of what it's producing here. You'll notice that it's producing a nice sort of like user interface window. In fact, those are sort of interactable, so I can actually, these are things that I can interact with and sort of, presented in a nice sort of way. First, in terms of it's giving us some basic information, so our classifier is using the method of logistic regression, and there are 20 samples that we're testing, that we're producing these measurements on, right? That's the size of our testing set. And the accuracy is 75%. So what that means is that of the 20 test samples, exactly 15 of those were correctly classified. So 25% of them were misclassified. Now there's this notion of baseline accuracy. How good is 75%? Right? Maybe that's good, maybe that's bad. If it's for sort of classifying images, that's probably fine if it means that it's work that I don't need to do, and if it's not a mission critical scenario. But if you're trying to, for example, classify whether or not, if this is a context of a self-driving car, for example, an accuracy of 75% of identifying red lights, for example, is probably absolutely unacceptable, right? So it depends on what you're trying to do. But one way that you can sort of get a sense of how good accuracy actually is by comparing it to the baseline accuracy. So what does that mean? Well, we have 4 classes in our in this problem, right? These 4 characters. So if I just picked at random, I would expect to be able to get a 25% correct answer. Now, in fact, it goes beyond that. Here we have this baseline accuracy is more than that. Reason being that 40% actually corresponds to the size of the largest class in our testing set. So because we split up the training and the testing randomly, we don't have a guarantee that it'll be 5, 5, and 5, and 5. It might be more or less. And in fact, that's what this baseline accuracy corresponds to. So one of the characters will be more common in the testing set. And if we guessed that character all the time, which is to say we've not learned anything other than just which of the 4 classes is the most common one, then we would have a baseline accuracy of 40%. So that's what baseline accuracy is. Now there's some other statistics here, but perhaps I want to maybe just go over what this here is. In fact, we can actually extract those individually if we call the classifier measurements function with a particular element. And in fact, you can I'll let you go and look at the documentation for classifier measurements for the list of all the different measurements that you might be interested in getting out of this function is. But so yes, accuracy, the confusion matrix is the name of the plot that I wanted to go over. So what that corresponds to is showing in a matrix what, well, in fact, if I just hover over a particular element, it'll say in plain English what that is. So here I'm focusing on the top left element of this matrix, where the row and columns are both labeled as Gomorrah, and it's saying that there are 2 examples of Gomorrah that were correctly classified. So in our testing set, there were 2 examples that, as you'll see on the left here, actual class was Gomorrah, and the predicted class is Gomorrah also. And so actually we want, ideally, everything to be along the diagonal. But if we sort of see how there's a sort of a 2 written here on this as a summary for that particular row, there were 2 examples of Gomorrah in the testing set, and there were 7 in Groot, right? And that's where we're getting this sort of 70 from. If we do this 70 divided by 20 times 100 to get a percentage, and then a numeric result, that's where we get our 35. Oh, no, the Star-Lord is actually the most common class. I got that wrong. So this is Star-Lord, right, where you have 8 such examples, right? And so that's where we're getting our 40% from. Great, and so here, are examples of, in the bottom left, we had Star-Lord was misclassified as Gomorrah. Now, the reason that this is relevant is because this can inform how well, in a more precise way, how your classifier is behaving on data. So I know from memory that there are some examples from in the documentation for the MNIST database. So here's an example of a larger confusion matrix from the MNIST database. So that's to say these handwritten digits. And we're seeing that it's, we want these to be our longer diagonal. And you'll notice, for example, that here we have sort of a hotspot. Let's see. So this 81 here. So there are a lot of examples here of 9s being confused for 4s, right? So reading in the columns and rows. And, that actually makes sense given how the 9s and 4s are actually quite similarly shaped. And so this can inform us as to how well for particular classes our classifiers behaving, and that might inform that we actually want to produce more examples from our data set. We might want to go and collect more data to sort of improve the performance, so it can actually so that our model can learn more about the difference between these different classes. And we can also ask for sort of the worst classified examples. And again, that might inform us that we want to produce more data or change your model accordingly, or the best classified examples. And these are using the probabilities that we've seen earlier to sort of identify the ones that are over which the model is most confident. Great. So methods. I actually don't want to necessarily spend too much time on that because I think that the point is to show the sort of the overarching way to go about machine learning and artificial intelligence in the Wolfram language. But the point is that there are a lot of different methods that exist for this. In fact, this document is we're a bit too zoomed in for our needs here. So what we're showing here is we have some data, and we're creating classifiers based off of these points here. They are visualized, so there's a two-dimensional input, so no need to do any feature extraction. There are already numbers, and the labels are just 3 classes, so red, green, and blue. So if we create a classifier function and we try and sort of fill in the rest of, we'll see that basically the different methods, right? So we have nearest neighbors, and that produces, this is what how our nearest neighbor classifier performs on unseen data points. And so sort of filling in a sort of, it literally is producing the nearest neighbor. So if we're sampling this point right here, that'll actually just find the k, so where k is some number, 3, 5, 7, depends on the data that you're dealing with. It'll find whatever points are nearest in this feature space, and then do a sort of a vote of popularity. So we get these sort of boundaries that are quite strongly connected to the data that we have. Whereas if we use logistic regression, the boundaries are actually going to be a different shape. In fact, I believe that with logistic regression, they're going to end up being linear. There's going to be a straight line between the different classes. Or if we use support vector machine, that's going to behave differently. Or random forest, so there's these sort of decisions that are taking place. These actually cut up into different regions differently, or naive Bayes, or in fact neural networks. And so all of these produce sort of different types of classifications. And again, if you want to specify these, let me just change, I'll change the zoom later. You would actually go about specifying this when you create your classifier function by calling the classify function. That's quite a mouthful, actually. So the classifier function is the result of calling the classify function. Great. So when you call the classify function, you can specify the method. And by default, if you don't specify, like I do here, it sort of goes to automatic by default. But if you want to specify something yourself, you can go ahead and do so in that way. So I can say I specifically want to use logistic regression. And you can go and, there's entire textbooks written for each one of the methods individually and how they behave and how they don't, their limits and how they work. But it's worthwhile mentioning that, if I leave this to automatic and actually just give it a time goal of, say, 30 seconds, just to show what's going on, the process that you would go about to figure out what method is adapted to your needs is sort of iterating through different things and trying different methods and seeing how they perform. And that's actually exactly what's going on when you leave the method going to automatic. See, it's sort of trying out a bunch of different methods, and its current best one is gradient boosted trees, but it's sort of it's doing the process that you might do. And there's a lot of different things that you might want to play around with, but that's perhaps a bit beyond the scope of what we're going over here. And in fact, actually, we'll spend a bit of time going over that. So choosing the right method, right? So right. The question is not necessarily how or why does it work, but does it work? It's very empirical. There's sort of think of machine learning as rather a black box sort of scenario. So you really want to just test it empirically on the data to see what works and apply it to, that's sort of the idea. Now there's a quick example here over this this Fisher iris. This is another standard data set, so it's actually built into the example data that we have within the Wolfram language. There's the different classes again, and you can see how these two different classifiers perform. So here we're producing a Markov classifier. Here we're using a random forest classifier, and then we're going to sort of run the classifier measurements on each, and we can see maybe one performs better than the other. So they have comparable accuracies, but maybe one of them is more in line with. So there's a different number of criteria that we want to make use of. And so here, what we're doing yes, we are doing it on the testing data set. But yeah, so in terms of choosing the right method, it's a sort of it's a whole art in its own right, and there are methods and plenty to go over. But yes, well, that's all I want to say about that. Now, prediction. I mentioned these. So this is prediction as reminders again, as opposed to classification, right? So classification have discrete classes, and prediction have sort of a continuum of numbers that can be predicted. So as an example, here we have this the Boston home. So this is data about house prices in Boston. In fact, let's here take a quick look of what that looks like. So here are all the columns in our data set. So there's a bunch of different criteria that we might be able to use to predict. In fact, the value that we're trying to predict is the median value. And so here again, we're sort of breaking up into training data and testing data. And again, what makes this be a prediction task rather than a classification task is the fact that the value itself is going to be a value that changes continuously rather than discretely. It's not a yes or no. It's not a which of the 4 characters. It's what number, and that number can be any number of things. And so similarly to what we did earlier with the classify function, here we're using the predict function, right? So we do predict on our data set here, and I mentioned earlier about data set as a construct to hold data as opposed to lists or associations. And this is nice because we can sort of say, here's our data set, which in fact, let me just pop it here to get a view of what this looks like. So again, we have our different columns here and with all the different numbers in it, right? And we just need to say, this is the name of the column that I want to predict, right? So this very last one. And again, this is, just to show that this is some nice syntax that's rather terse to get things going. And yeah, and so this creates, analogously to classify, creates a predictor function that we can then immediately make use of, just like a function. Now, mind you, these are in thousands of dollars. So the estimated price for this house with these various criteria is of 19,000. So I think this data set is rather old. I would quite like to be able to buy houses for that kind of price in Boston. But similarly to classifier measurements, we also have predictor measurements. And instead of having a confusion matrix, we now have a sort of a graph on the x with the predicted and on the y with the actual value. And ideally, we want everything to sort of lie on the diagonal. And we can see that there might be some outliers. And again, we might want to inspect particular samples to see where we might need to get more data. But again, all of this is rather similar and analogous. So yeah. That's what's going on with prediction. They have very similar concepts to classification. I see a quick question from Kareem about classifier measurements not producing the confusion matrix that was expected. So let me just scroll back up to that example, which was from earlier. Yes. So here we're doing in classifier measurements. I'm not sure exactly what you've done, Kareem, on your side, but typically the way that I would go about here, we've sort of stored the results of calling this classifier measurements in a variable, right? And then we've specifically, let me just delete this output so that we can sort of see it. And then we're invoking this particular elements of it. And there's some, one thing which I encourage users to follow when writing code is to follow the convention that built-in functions start with a capital letter, and functions that you define or variables that you create start with a lowercase letter. And this is particularly confusing here because this classifier measurements is a built-in function, has a capital C, and then we're storing the results of that in this lowercase c classifier measurements, right? And then we're calling classifier measurements on we're accessing this object and we're getting this particular component of that object. So maybe I suspect that might be one of the reasons, Kareem, that you might be encountering issues with getting the confusion matrix plot working. But with that being said, you can also call the classifier measurements function with a third parameter, I believe. I do hope this works. Yes, indeed. In fact, the auto completion is helping me out here. And so I can say, I don't care about all of this sort of summary that we saw earlier. I just want the confusion matrix. And you can go ahead and do that here. And again, I encourage you to go look at the documentation because it explains all the different things that you can do, and it shows examples of exactly how the correct syntax to go about it. So yes, again, documentation I'm quite fond of. I hope that helps out. Great. I think let's move on now to neural networks. I just wanted to go over this. There we are. So neural networks. So neural networks are effectively they're a method, right? We saw that there was a list of different methods that existed. So random forest, k-nearest neighbors, and neural networks are just another method. And the reason that they're interesting is that they're actually quite general, and they're very parametrizable. In fact, they are universal approximators in some sense of some technical definition that what that means exactly. But we have a bunch of functions built into the Wolfram language that allow you to define, create your own neural networks. And so here what we're looking for, in fact, this doesn't work, so I'm going to use different syntax. So information, where I'm going to provide a string, and this is a regex style. What this says here is I'm looking for all functions built into the Wolfram language that start with some that contain effectively the words or the characters layer exactly as is somewhere in them. So, for example, aggregation layer or graph layers with a capital plural. So these are all the functions that are that contain the word layer, and typically they are related to neural networks, right? So these are different kinds of layers that you can produce. So softmax layers, for example, those are for producing probability vectors. There's going to be convolution layer somewhere, convolutional layer or convolution layer. So all these are sort of built in, and they all have their own particular uses, and you can build your own custom networks that way using the net chain function. But you don't actually need to build, this is all kind of beyond the scope of what we're going to have time to cover today, but you don't actually need to construct them yourself because you can get them directly. So, net model, you can create a net model by directly giving it a name. And this uses, again, the neural network repository and returns a net chain object, right? So if you wanted to construct your own neural networks, you could go about calling the net chain function on a list of different kinds of layers, which you can also give names to. And then, here we're specifying them on an element-wise layer, which uses a ramp function, and then a summation layer. And again, this is a very simple layer, very simple net chain, but you can imagine it getting very complicated very quickly. And in fact, if we look at the LENet, it in fact has a big number of, well, it's actually, this one isn't too tricky, but it starts off with images that are 28 by 28, and then brings down to the softmax layer, which is producing these probabilities, again, probabilities with inverted quotes, using softmax layer and a bunch of pooling and flattening and linear layers in between. And what's neat about this is that here, so let's just create a bunch of, here we're using, again, this our data set to extract a sample of, let's just show the first 3 samples, right? So we have 3 such samples. And here we're sort of testing it on, so here we're actually making use of the LENet to predict the classes, and we're seeing that it probably gets most of them right. Let's see if it gets any of them wrong. No, it's got all of them right. Well, let me just reshuffle it to see if we get any different results. 22222792414. Looks like it's gotten all those right too. Oh, wonderful. But yeah, eventually it'll get some of them wrong. But one of the things that works, what I wanted to show here is that we can sort of take these samples and we can apply a blur function to them to sort of make them a bit blurrier, and we can try and sort of test how it works on those, and maybe it doesn't perform quite as well. I think it's gotten most of it. So it's confused this 4 for a 2, for example. What we can do now is we can retrain the network, right? So not only is the network already existing in the sense that all of the the structure of it has already been built in, but we can actually change the weights themselves that are associated with the model by retraining it just on the data that we want. So here what we're doing is we're calling nettrain on, again, the model that we stored in a variable, but with our own data set. And in fact, here we have these sort of learning rates. So that's showing how well it's performing. And this takes more time because, in fact, there are quite a few weights in the network itself. And I think it's worthwhile. I'll mention this a bit later, but there's in terms of, insofar as this does take time, there are relevant things in terms of what method and sort of in terms of performance CPU, GPU that I'll mention in just a moment. But once we've gone ahead and retrained our network, we can then see if it performs any differently on our data set. So let's see, the 4 here got confused for a 2, and now it's getting that right. So we've retrained our network on a new data set. And do be mindful that as you retrain, since here we're only including the new data, it'll sort of over time lose the information or lose its ability to correctly classify the original data set. So if you're doing this in practice, you're probably going to want to join it with the existing data. But if we, for example, in the case of when we were looking at the confusion matrix, we saw that there were certain classes that were being incorrectly classified, then we can go ahead and include more data as we see fit. And so here what we're doing here is we're using a new font, right? So we're using Comic Sans this time, and we can see how well it performs on those, and it seems to be doing not too bad. I think it's gotten most of those right. Yes, and it's still, as I said, was doing relatively all right on the original data set, even though we've retrained it. It hasn't entirely forgotten, but it will do so eventually if we, if we continue training it. So here we've taken, and what we've just shown, we've taken an existing data set and we've retrained it. But what we can actually do is we can take an existing data set and then break it apart and construct a new one, modify or adjust as we see fit. So this LENet, which and this is the power of sort of having a symbolic representation for neural networks, right, where they're objects that we can reason about and do operations on. So here we're actually showing the underlying representation for this model. So in fact, here we're getting back the list of different layers that exist. And why is this great? Is that we can actually just ask for the first part of the layer. So here, this is the first layer is a convolutional layer, and we can just extract that particular layer, and then we can see exactly what's going on, the weights and biases, right? So here the biases are built in, and then we have the weights here. So those are numeric arrays, both of those. And here we're actually going to show how you can make use of that to sort of get a glimpse at what's going on under the hood. So here we're using the image identify net v1, and that's one of the built-in models that we make available. And what this does is I think I forgot how many classes there are in the Wolfram, let me see, 4,000 classes. So that's the example that we showed with Guardians of the Galaxy had 4 classes. Here we have 4,000. So we have 4,000 classes, and one of those is Tiger, and that seems to have correctly identified that. What we can do is we can actually call take, which is to say, on this image identify model, we're going to, let me just show that sort of on its own. We're taking just the first 10 layers. So here, this net chain has all of these different layers, right, all the way to finishing off with a soft max. Oh, 4,315. Not 4,000. Or maybe the 4,000 was meant to be more of a vibe than it was an actual number. But yeah, so we've done this take on this image identify model. And now what that means is we're just taking the first 10 layers. So we've literally just, in the same way that you take a list and you say, I want the first 10 elements, we've said, I want the first 10 layers of this neural network. And once we do that, we can still call it on this image here. And what we're going to get is this, we've sort of, we're peering into just that particular aspect of the neural network. So here we're going to have 192 by 55 by 55. These are going to be black and white images, presumably. Well, in fact, we're just going to, here where we're in fact just taking the previous results, right? So maybe this makes more sense once it's shown. Effectively, we're taking our neural network and we're seeing what the network sees in the middle of it when we're passing in this image. And and this is how the sort of some of the hallucinatory images that have been created about sort of seeing the most cat version of an image, or what the network thinks is the maximally cat. That's kind of what's going on here. So you can maybe theorize that some of these images correspond to maybe freeness, or maybe patchiness, or maybe sharpness, or yeah. So that's kind of what's going on here. This is kind of neat. Maybe if you're trying to understand what's going on, it's not necessarily all that insightful. Maybe here we kind of still have some of the original structure. Maybe we have different things here. But the reason that this is relevant is that we can sort of then actually construct new neural networks by starting off with just the original layers and then adding on just what we want at the end. So this is showing how we can, programmatically get access to see how there's sort of progressively smaller and smaller images. So we're starting off with, I forget how large the input layers are of these images. They get normalized too, but at the end we have these 4,315 classes. But yeah, so you can in the case of MNIST, for example, one example that we have in another webinar that I'm familiar with is where we're taking the MNIST database, but we're then trying to retrain it on similar black and white handwritten digits to classify no longer digits, but characters that are going to be in different, not languages, but they're going to be Roman characters, or they're going to be no longer digits, but they're going to be letters, right? So classifying whether something is a digit or whether it's a character, right? So you can build off of the pre-trained network and all the information and structure that it might have gleaned, right? So you can do retraining in that kind of way by being able to symbolically represent what a neural network is in the Wolfram language. So briefly, I'd like to mention about overfitting, because neural networks are great and they're very generalizable and they represent a lot of different things. But there's this notion of overfitting, which is worth being mindful of. So what does overfitting mean? Well, here let's sort of give a sort of an intuition for what that looks like in a sort of a more simplified example of trying to fit data to a curve, or fitting a curve to data. So here is sort of our same. We have in this first image here that I'm looking at, there's a bunch of samples, right? These are represented by blue dots, and they sort of are spread around in different ways. And we have a sort of a true function that actually generated this. And this to me, this looks like this was some kind of sinusoidal function, so a sine or a cosine. So it was sampled from that, and then some noise was added onto it. Now, if our model that we choose to try and fit is a linear model, so just a very simple regression, then we'll see that it does a decent job of sort of capturing the general downward slopeness trend of the data, but it's failing to sort of capture everything. And in fact, we have a mean squared error that's relatively high. If we instead fit a degree 4 polynomial, we're getting something that's much more close to the true function. But if we keep increasing and we go to a degree 15 polynomial, then we're starting to get, it's actually from a mean squared error, right? So we're going from an error of 0.4 to an error of 0.07 to now an error of 0.005. So we're from a mean squared error perspective. So how much wrong we're classifying, this is kind of the accuracy that we were talking about earlier, right? We're doing better, but we're doing worse in the sense that we're now matching to noise. And as soon as we go outside of the samples from our training set, we're getting much worse performance than we had on degree 4. Now, this is a nice picture. It's not necessarily super representative of, it sort of gives the idea of what overfitting is about, right? So as you make your model more and more general, more and more expressive, it's going to start being able to match the noise. Well, it's going to be able to match the training set exactly, right? And it's sort of doing this rot memorization. But that doesn't mean that it's sort of getting at the essence of the information that we're trying to glean from the data set itself, because it's starting to match to the underlying noise that might be in the measurements, right? So that's sort of the idea behind overfitting. Now, this is quite a tricky, it's a very deep problem. There's a lot of different things that we can try and do this to try and solve this. So here we're sort of another example where we're dealing with some the data that's following largely this sort of exponential decay. Right? It sort of looks like a bell curve, effectively. If we do if we create a neural network and we train it on that data, we'll see that it'll. I'll have to let this run briefly. We'll see that it'll be a lot noisier than the actual underlying data, which is a rather simple function. So let's see. Yeah, so it's very noisy, and it's matching all the points very well, or most of them, but it's not actually getting at the essence of, our function is strictly positive and it's predicting negative values, for example. Even though some of the samples being negative is a part of the data set, but it's not what we want. So how do we avoid overfitting? Well, one first idea is regularization. So what regularization is insofar as the neural network, as models are more expressive and allow for being more precise, we want to sort of give a penalty to making use of those parameters. So that's sort of the idea. The more complex the model is. So that is to say, as the weights and the biases get bigger and bigger, we want to penalize that. So the score that the training process is trying to optimize is trying to reduce the error in terms of the prediction, so making its predictions match the data from the training set as best as it can. But now we're also telling it maximize that score whilst also being penalized or getting some negative points for making a model that's complicated. So that's what regularization is. Now, there are different ways of going about defining the penalty score. So there's L1 regularization, there's L2 regularization. You can do a combination of the two. Sometimes that's called ridge regression, for example, right? So there's a bunch of different methods that are included in that. But once you give a penalty, oh, is that actually the train? That looks suspiciously good. Well, yeah, regularization does work quite well. But yes, so this is showing our neural network. Again, we haven't changed the structure of it. It's still the same architecture, but we've just penalized the weights in such a way that it's forced to try and do more with less, right? We're penalizing it. It's not quite so free to go about and tweak its parameters to its heart content and to try and match every single data point. And so indeed, we're giving up accuracy. We're performing worse on some data points by not fitting all of them, but we're still getting at a better result from a qualitative standpoint. Another attitude or another possibility is to use sort of dilution, or sometimes called dropout. And so here, the way that you would make use of this is by adding a sort of a dropout layer. And so here, what this 0.8 means is that effectively and randomly, notice how these learning curve, the loss curve here is a lot more jagged, because effectively we're introducing randomness. We're saying at training time, and I forget if there's also a time where we're actually using the neural network itself or not. But we're dropping out some weights. So we're saying, oh, this particular input, in fact, also not just inputs, but sometimes intermediate weights or nodes in the neural network will just get removed. And so that it makes it impossible for the network to just rely on individual bits of input. And so it's forced to look at different aspects of the data to make its classification or its predictions. And then we see that this performs maybe not quite as well as the previous method of regularization in this particular data set, but it is perhaps being a bit more smooth, at least on the right-hand side of the curve. And last method that we're going to cover over here is that of validation. And the idea here is that instead of just splitting up our data in terms of training set and testing set, we're going to break it up into three. So training set, validation set, and testing set. And so what that means is that, in fact, let me just run this net train again. So we're seeing that there are now two curves. There's the training set in orange, which we're seeing is decreasing, but there's also a validation set. And so the idea here is that when we're doing this training, let me just run it again so we can see because it's nice to see things move. The validation set isn't being used to train the neural network itself, but it is being used to figure out when it is that we might want to stop training. And so we're sort of trying to detect when overfitting is starting to take place. So initially, both of the two, both the training loss and the validation loss in decrease, which is to say we're doing a better job of correctly predicting the data. But eventually, it's only the training loss that starts decreasing. So we're sort of starting to learn the inherent randomness of the data rather than the sort of the overall trend. And so we're stopping early effectively. Instead of saying, oh, we're going to stop when we're going to take our last version of the neural network, we're actually going to take a version which was, we're going to stop early, because here we're sort of fitting to the noise rather than fitting to the actual data. And so that's what using this validation set is all about, right? So we actually split it up into three different bits. And there's a number of other techniques that also exist that we haven't covered here today in terms of how to combat overfitting. But all these can also be used together, right? So you can both use a validation training and testing set, and use dropout and dilution, and also use regularization. In fact, this is very common that all of those are used together. Yes. Now, with that being said, there's a lot more to go over in terms of how neural networks can be constructed and how to train them, and that's just a sort of a cursory look into what's possible and how you'd go about it in terms of the style and syntax within the Wolfram language. But it goes much more than that, much deeper. But yes, as a summary, as a conclusion to what we've done today, all of these functions, I hope you've been convinced, are very easy to access, right? It's just classify and predict, and in fact, you don't even need to build your own classifiers or your own predictors. In many cases, you can use the ones that are already built in. And you've also got feature extraction, but again, those are sort of built in. And there's a bunch of different choices of methods, and we support and have built-in functionality for many of them. But again, if you don't specify your own, the Wolfram language will make some choices for you. And in fact, I think it's worthwhile sort of going over an example of what that looks like. So if I go to the classify method and I look at maybe a not so trivial example. Let's see. So this is dealing with the Titanic dataset. So this dataset, in fact, let me remove this semicolon. So this semicolon means that the data is not shown. So maybe I will actually, yeah. So this is showing as inputs we have the class of the passenger, their age, and their gender or sex. And so this data set is then what we're trying to predict is whether or not they survived or not. That's this particular data set. In fact, actually, we have a nice little way of visualizing what that data looks like right here. Right, so we have the first a random sample of 10 of those rows in that table. And if we, in fact, train our classifier and we specify a method, it will, in fact, just use logistic regression, right? But if we don't and leave that to automatic or just omit it entirely, and we give a time goal of, say, 15 seconds, we'll see that it's trying out. In fact, let me just give it a bit more time than that. I tried to do interrupt, but it's let's give it 60. But I need to do evaluation, abort current evaluation. I usually use the keyboard shortcut, but I'm on a different platform than what I'm used to. But yes, we can actually see if we make use of the different tabs here, we can scroll around and see the learning curves for all of the different methods that it's making use of, right? So here it's making use of a bunch of different methods. Here, the current best one is the random forest method, and it's testing them and making use of different numbers of training examples and comparing how they generalize or not. And really, this is quite powerful because if you want to go, if you're trying to prototype something, just get a quick idea of whether or not something works. And in fact, when you're doing doing machine learning, depending on what you're doing, being able to iterate very quickly is quite valuable. You can just spin some experiments up and have some choices that are made for you automatically quite smartly, because it's doing a bunch of all the sort of the expertise and knowledge that we've built as a scientific endeavor collectively has been in part distilled into these functions, into classify. So there are a lot of sort of pitfalls that such as overfitting. There are many others, right, that you might fall into, and classify can help to mitigate some of these. Or it makes choices automatically they're not unreasonable most of the time. And I think that's one of the real value propositions of making use of the framework that we have here in the Wolfram language for your needs of machine learning and classification.